Okay, I think we can start. Okay, so what I'm going to do now is a little bit of recall first. So let's recall. So last thing we proved was this Boyle integration formula. You remember? So the idea was that you have an invariant function, and if you want to integrate it over this Hermitian matrices against this Gaussian measure, this you can reduce it to an integration over n-dimensional space. So there was a constant Cn integral over Rn, and then it was f of lambda. We had the product of lambda I minus lambda j squared, I less than j. There's this Vandermonde factor squared, and then mu lambda 1 mu. So let's see. So here f from Hn to C is an invariant function. So unitary invariant function. In this thing, then of course the measure the mu h, you remember, was this Gaussian measure, which is exponential of minus, well, it should be normalized. So 1 over Zn exponential of minus 1/2 trace of h2 dh. This is the Lebesgue measure, but this is the Gaussian part. It makes it convergent at infinity and all that. This f of lambda, so here lambda is the eigenvalue matrix of H. So this is like lambda 1. And, but this is just a variable here. And there is no order in this case, so this is lambda 1 lambda n. Just dividing by n factorial, take care of that. This is clear, and then I have to define this d mu lambda is also a Gaussian on the line. So this is 1 over root 2 pi exponential of minus 1/2 lambda squared. So these are products of Gaussians in Rn. So this is the standard normal Gaussian vector Rn, this distribution product of this thing. Right? So this is what we proved using change of variable formula, and then we computed a determinant. Right. Yeah, okay. So as I said, so this, we know that this product of lambda I minus lambda j squared is just this determinant of Vandermonde squared, 1, 1, 1, lambda 1, lambda 2, lambda n, lambda 1, n minus 1, lambda 2, n minus 1, lambda n, n minus 1 squared. Okay. So then to use this, we introduce these Hermite polynomials. So what are these Hermite polynomials? So this is a sequence of polynomials like h k of x, k from 0 to infinity, that has is uniquely defined by the following properties. One property is that this hk is a monic polynomial of degree k. hk is monic of degree k. And the second property was that they are orthogonal to each other. Inner product hk hl is equal to 0 for k different from. Well, this inner product, you have to be careful. This with respect to the Gaussian weight, not with respect to the Lebesgue measure, because polynomials with respect to the Lebesgue measure, they're not even integrable. They're just there's no conversion. But with respect to Gaussian, every polynomial is integrable. So this, I mean, fng, in this case, by definition, is integral over r. Again, we have to normalize, so just f g bar exponential of minus 1/2 x squared dx. If you don't even have to normalize, that's okay. It's an L2 product. So it's a way. So and in fact, what happens is that they form a Hilbert basis for this space. And K that form a Hilbert basis for L2 of R, and this measure exponential of 1/2 x squared dx. Yeah, so and then there was another property which was also crucial. That the property was that basically, yeah, so hk and hk, the length of these vectors is exactly k factors.
Oh, and the inner product with
Yeah.
F and G isn't F the one with the complex conjugate since it's on the left?
Yeah, so if you're a physicist, indeed, you would put it on the left, because for physicists, the inner product is always sesquilinear in the first variable and linear in the second. Mathematicians use the opposite notation, which is linear in the first variable and sesquilinear in the second variable. So there is a polarization of notations. I believe actually physics notation for bracket notation, the physics notation is more reasonable, but we don't use bracket notation in math. So we just use this. So yeah. Okay.
Oh, is there also a d lambda by the d mu lambda?
Which one?
Oh yeah, just right there. Yeah.
Oh, here is that. Yeah, it should be d lambda. Yeah, exactly. Thank you. Yeah, excellent. There's d lambda over. Yeah. Excellent. Yeah, very good. Thanks.
Thanks.
Yeah, this is normalized, but I don't have to normalize this because I'm just thinking of L2 inner product. This is now there are different ways to construct this. One method was I mentioned these are eigenfunctions of quantum harmonic oscillator. Yeah, but there's a much easier way actually to construct them. How to construct them? You can just argue like this. You start with this sequence of functions. So this is a sequence of functions in L2 of here, e to the minus, and then use Gram-Schmidt to this sequence. Okay, so apply Gram-Schmidt process. To this, with respect to this inner product, and then you get this Hermite polynomials. The only thing is you may not get the monic ones, but you can always divide by the coefficient of the leading term to get the monic one. And in terms of proving formulas, pretty much everything. Now, because this sequence is dense in L2 of this guy, it means that the sequence of Hermite polynomials you obtain is actually Hilbert basis, except for orthogonality, orthonormality, which you can fix it by dividing by a square root of k factorials. I believe this actually gives you everything, but maybe there is some recursion formula that would be hard to find using this method, but even the recursion, you can get it by this method. So everything you can basically use, apply this method, Gram-Schmidt process, which is very, very nice process, very useful. Okay, so
that meant polynomials universal.
Universal in what sense?
If we have, can we have another set of polynomials which will satisfy the same equations?
No, we don't get the same.
Okay.
No, we don't get the same. No. Actually, I will come back to that because we're going to change the weighting function to something more general. Then we get something called generalized Hermite polynomial. They are important as well. But if you apply this to other sequences, wait a minute, I have to be careful. No, I don't think you get the same sequence.
If you have a different sequence of polynomials, like can we have such a sequence which will also satisfy these three properties that they are each is monic in HK and form an orthogonal?
Yeah. As long as they are linearly independent, Hilbert-Schmidt always gives you an orthogonal basis for sure. So the span of these orthogonal things is the same as the span of the original linearly independent things up to any stage n as you move on. So you can just right, and actually that's the way you prove existence of bases for separable Hilbert spaces without using Zorn's lemma. You can always prove in the separable case that the Hilbert basis exists and you don't have to use Zorn's lemma. But in the inseparable case, you have to use Zorn's lemma. There's no explicit constructive process. So why we discussed that? Let's see. Oh, yeah. So now, so today we want to so one of the things we want to compute some integrals using this. So here is a lemma. Maybe I write the lemma there. The lemma is that integral over Rn. This van der Monde factor product of lambda and which is squared I less than j d mu lambda 1 d mu lambda n is actually equal to n factorial inner product h0 is 0 h1 h1 all the way up to hn minus 1 hn minus 1. Okay. Proof. The square of the determinant, and this expression that we have over there. Oh, so yeah, something also last lecture we proved that this square is equal to same thing squared, but replacing lambda i's with Hermite polynomials of lambda. You see, you can write it as so yeah, this is 1 1 lambda 1 lambda n lambda 1 n minus 1 lambda n minus 1 squared. You can write it actually as h0 of lambda 1 all the way up to h0 of lambda n, and then h1 of lambda 1 up to h1 lambda n, hn minus 1 of lambda 1 up to hn minus 1 of lambda n squared. This is what also we observed last lecture. And this does not use, up to this stage, we don't use orthogonality. We just use the fact that hk is a monic polynomial in lambda of degree k. And we use property of determinant. All the things of order less than n or less than k drop, they are junk, and this remains. Okay, so if we sub this in the integral, here for this, you sub in these things, expand the determinant using Laplace formula, which is this standard formula for expansion of determinant in terms sum over the symmetric group. And we just use the orthogonality relation. You see, all these things actually drops, so you get terms like this. Let me wait here now. Yeah. Yeah. So then only polynomials of the form yeah, it's 0 squared lambda sigma 1 up to hn minus 1 squared. Contribute. There are n factorial of those, and they are exactly equal to these terms after reordering. Contribute. I mean, this is So this is really nothing short of magic. I mean, it's really incredible because here, all these terms, well, I mean, it's not so drastic maybe, because if you look at this, if you expand it, you get only polynomials in lambdas. So the variables can be separated actually. So, and then you can integrate individually against each of those. So maybe it's not so bad, but knowing exactly what the value is, that's hard. And this is what is achieved by this formula. Yeah. And this is the essence of orthogonal polynomial method. This formula is the essence. Okay, good. So the corollary is the volume of unitary groups. That's what we can do. So the volume of the unitary group volume of UN is actually a beautiful formula 2 pi the power n squared plus n over 2, I think, divided by product of all factorials. Okay, from 1 to n minus 1. Okay. It's this is what we didn't know, and now we can compute thanks to this calculation. Now, as I said before, we have to be careful and know what they mean by volume of the unitary group with respect to what measure, because there is a normalized Haar measure on the unitary group because it's a compact Lie group of dimension n squared. So the normalized Haar measure has volume 1. So that's not a big deal. But here the volume is measured with respect to a multiple of the Haar measure. Which multiple? So there is a killing form on which I discussed last one of the previous lectures, killing form on the Lie of UN, which is the unitary. This is the unitary. I mean, skew Hermitian. So let me put it like this: I Hn. These are the skew Hermitian invariant matrices, and the killing form here is if you have two such matrices, it's minus trace of x1. So this gives you a positive definite inner product on this vector space, which is the Lie algebra of this Lie group, and then it gives you a metric, Riemannian metric by left translation, which is going to be right invariant as well, because the space is compact. And it is with respect to this that we are talking about the volume. We have to be very clear about what we mean by the volume. This is okay. So this is a consequence of Weyl integration formula and this calculation. Let me briefly indicate how. Oh. Put f of h equal to constant function 1 in the Weyl integration formula, right? And then we get the identity that because the left-hand side of the thing is 1, because you are integrating constant function 1 of this probability space. So the left-hand side of the WIF gives you 1. And then, so this gives you that 1 is equal to Now that the constant Cn, this integral over Rn, product of lambda I minus lambda j squared, product of d mu lambda I, right? Now, this Cn, we can actually elaborate a little more on Cn. You see, Cn is the volume of this UN bar, essentially. So this is basically volume of UN over 2 pi to the power n squared plus n over 2 times the n factors. You see, in the Weyl integration formula, to prove that we used a map from UN bar, from Dn cross UN bar to Hn circle, right? We use the diffeomorphism. What was this diffeomorphism? This was the Weyl chamber. So this basically lambda cross a class of, this is the course of the space, homogeneous space. It was mapped to basically U lambda U inverse, where U and bar is UN mod Tn. This is the maximal torus. There, and this is, so this part of this factor is the volume of the maximal torus, 2 pi to the power n, actually, because the torus is a product of circles, and the circles may take measure 1, they are radius 1. N factorial is because we replace the n by Rn. So because these are all ordered, lambda 1 less than lambda 2 less than lambda n, but in Rn we are integrating over it. So this is this normalization factor. And the rest of this 2 pi, this thing, is because of computing the Gaussian over Hn gives you these factors like this. And so basically, you see volume of UN bar is equal to volume of UN divided by volume of En with respect to that inner product. So in any case, we have this. So sub in here, star, and use that lemma. And use radius lemma. Of course, with the calculation that we know that this is n factorial times 1 factorial times 2 factorial times 3 factorial times n minus 1 factorial times n factorial. So we get. So this calculation is interesting, is a nice application of Weyl integration formula. But I mean, this formula is beginning of a lot of developments in mathematics. So you can see just a bit of it. That's all. Yeah. Okay. Now, one of the things, okay, so another immediate calculation is this Zagier theorem that I mentioned. I indicate how to prove it, but maybe I won't be able to prove it completely today, but let me indicate this. Let me indicate what it is. So we'll have two Zagier theorems. This one is the easier one. But the main one is the one that is computing the Orthogonal Euler characteristic of modular spaces, which is curves, which come from about in about 1 week from now. Yeah. So let me maybe put it like this: the R's are here. Theorem 1. So let us recall that what some notation and what we are after. Recall. So we introduced some combinatorial numbers, so epsilon gm is the number of genus G surfaces, basically the number of ways. Let me put it this way: number of ways to obtain a genus G surface by gluing an n-con. Two n-cons, sorry. Right? I mean, let's recall. I mean, we started it squared, for example, and go to 2, for example. And in this case, we got two things. If we have this, okay, so let's put this way. If we glue across the edges like this, then we do get a torus. And in fact, we get more than a torus. We get a one-face map, more than a torus. In fact, a one-face map. This one-face map means that there is the boundary here turns into a graph here. Turns into a graph with one vertex. Because in fact, by doing this, all these vertices, these 4 vertices here in the original graph, the boundary we are talking about, the 4 vertices of the boundary graph collapsed into one, gives us one vertex. Okay. Now, number of edges is always half of the number of edges of the original graph, which is n always. And number of faces is always equal to 1. So the Euler characteristic chi is equal to 2 minus 2g, but we know that is also equal to v minus e plus f by Euler's formula. So it gives us v, we don't know, but then we have e, which is n always, plus f, which is 1. So this v is the only unknown. How many vertices we obtain by gluing these vertices is the only variable in determining the nature of the genus of the surface, the Euler characteristic, or equivalently the genus. This now, there are 2 cases that we get genus 0, namely these 2 things. I'm drawing things that I already did before, so but that's okay. And then we also have another one. Again, a sphere. Yeah. So here is number of vertices. V is equal to 3. Here V is equal to 3. And this implies that G is equal to 0. So the in general, we get some polynomial Pnx. We introduce this polynomial Pnx, generating polynomial. Well, I use another notation Tn, but this Harzagir likes, and also Zwangi and Lando use Pn, so I just use Pn. So let P, yeah, Nx. So yeah, okay. So let me put N here. Sorry. Yeah. Yeah, this is N. Again. Yeah. Okay. So let Pnx equal to sigma x to the power v of sigma. So it's over sigma. So this we can also write it as sigma over genus theta equal to 0 epsilon g and x to the power n plus 1 negative 2g. Now, this sigma is the number of, not number, sigma is a gluing of this two and go. Sigma belongs to set of gluings or pairings of a two and go. I mean, this set, the size of this set is, of course, is the number of pairings of a set with 2n elements, which is 2n minus 1 double factorial. Right? That's 2n minus 1 double factorial is the total number of such sigma. So this is essentially, and this V is the vertex obtained by doing this gluing here, according to sigma. These are two equivalent ways of writing the same generating function. So this is a polynomial, and yeah. So and the power of x is at least 1. Cannot be. There's no constant there because it's vertices. There's at least one vertex here also. So then, yeah. So now the question is, what is this Pnx? So the goal is find the formula for Pnx. Yeah. So one of the things that we observe, again, if you recall, we show that if we compute the expectation value of trace of H2n, which is by definition is equal to integral trace of H2n, dv of H, right, over Hn. So this is exactly Pn n. But these numbers, yeah, I mean, so I mean, proof was based on Wick's we did this. Yeah. Yeah. So this simple observation, for example, here tells us that what is P2n, right? I mean, here, this thing, you know, tells us what P1n, P1 n is equal to n squared, P2n. Yeah, we start with that, but P2n is 2n cubed. That calculation shows that P2n is 2n cubed plus n P3n is equal to 5n4 plus 10n2 and P4n is equal to 14. Yeah, and 5 plus 70 n cubed plus 21. Now it gets complicated to compute these things, but we can make some general observations about them. Well, the leading coefficient, which is the number of ways to blow a 2m gun into a sphere. So that corresponds to genus 0 case. The leading coefficient corresponds to genus 0 for that, because you subtract genus. So that's the leading coefficient. So the leading coefficient is always equal to epsilon 0. I mean, okay, so how to put it? Epsilon g 0. Epsilon gn, that's my notation, right? 0. And squared. No, n to the power n plus 1, yeah. Right. This we know exactly is equal to Cn. That's the nth Catalan number. Which we calculated and we showed that it's equal to 1 over n plus 1, 2 and choose. So that's one observation. The second observation is that sum of these coefficients is always 2n minus 1 double factorial, because that corresponds to number of total gluons, right? So sum of coefficients, which is actually what is nothing but p and 1, you replace n by 1 here, that's equal to 2n minus 1 double factorial. And the third observation, which is easy, is that actually Pnn is, so P2n x is an odd function, and P2n plus 1x is even. So this is always, there's this pattern. Yeah. Okay. But beyond that, we don't know much. But now there is this magic formula of Harazagir that actually tells us what is this PNX. Rather explicitly, but it's not completely explicit. I mean, computing the coefficients from this formula is still a little bit of a problem, but that's a huge thing that they did. So let me just. Are there any questions? No. Okay. So let me now erase this. Write the formula. Here. So this is horizontal. Okay, I mean, I call it theorem one. I don't think in the literature it's named like that. It's called horizontal theorem. But I want to distinguish it from this and another theorem that we put in a couple of weeks. So this basically tells us that what is P and X in a rather explicit form. So P and X is equal to, 2n factorial divided by 2 to the n factorial. And then sigma p equal to 0 up to n. And choose p times 2 to the p. And choose p times 2 to the p. Okay, now that we just multiply x times x minus 1 times x minus p over p plus 1 factorial. Yeah. So each term is rather complicated. I mean, it's a product of this thing, and then you have lots of sums. It's a sums of products. So let's see. I mean, the corollary, just to see how glean information. So, what is the leading coefficient here? So using that formula star, we get that the leading coefficient of Pnx is equal to is obtained if you put p equal to n. Okay. So the leading coefficient is going to be 2n factorial over 2 to the n factorial, and then n choose n, then 2 to the n, and then x times x minus 1 and x minus n. I shouldn't say leading coefficient, but I should say leading coefficient appears in. So, n plus 1. I mean, which is equal to 1 over n plus 1. 2n choose n. X to the power n plus 1 plus lower order. So here again, it gives us a formula for epsilon 0, epsilon 0 n. But we calculated this, we showed this independently. So this confirms what you already know. It's actually interesting as an exercise to use this to compute the coefficient of next term. So exercise it is. Use a star to compute coefficient of x to the power. You see, if you put g equal to 1, you get n minus 1, which is just the epsilon 1. So this is the number of ways you would obtain a torus. Ways you obtain a torus. I was too lazy to do that. It's a good exercise. It's a simple thing. Yeah, you see, you have to add the x to the power n minus 2 from here, the x to the power minus 2 that comes from the next step. So, and then there is some cancellation, so we have to. Okay. Now, how this is proved? So, I mean, for the proof, I won't give the proof really because I wanna do something else. At least right now, I won't give it. But see, Landau is wonky, which they reproduce Harazaghi's original proof. But I just tell you that the proof is based on Weil integration formula. They use Weil integration. Or actually, yeah, or the proof given in Etinghoff is actually, I would say it's better. I mean, it's more straightforward. Or Etinghoff. Yeah. So this is in their, I believe, Invenciones 1984 paper. I think so, 85. Around that time. It's a very well-known famous paper. But they use this, they use Weil integration formula plus orthogonal polynomial. So Weil integration formula plus orthogonal polynomials. I'll read a little bit. Yeah. Okay. So, yeah. So before we leave this for now, there is one nice application of this Weil integration formula again, which I want to do it explicitly. So, yeah, this is called Wigner's surmise. Yeah. Right. Wigner's surmise. You know what surmise means, right? It's
Summary.
Hmm?
Guess, like a summary.
No.
Just a guess.
Guess,
Just-
yeah,
It's a
educated.
conclusion.
What, sorry?
It's just like when you conclude something, you put the pieces together and you conclude.
Yeah. Also means, yeah, I was thinking also educated guess or something.
I don't think so. I think it's more like it's right in front of you and you just don't, I don't think you do much work when you surmise something.
So it's, yeah, I don't know why I was thinking it should be related to guessing or something like that. Yeah. But yeah, if someone could look it up.
Supposition. Suppose that something is true without having evidence to confirm it.
Yeah, supposition that or supposing that something is true without having evidence to confirm it.
So it's like guess.
It's like an educated guess. Well, or guess, yeah. Yeah. But there could be that actually there are other meanings to it. That's not the only meaning, yeah. So yeah, so what is this Wigner surmise? So this goes back, I believe, to 1956. And so basically, this is pairs of random matrix theory. Yeah, so how random matrix theory was born, actually, it was born as a result of the following problem. In early 1950s, they had a lot of data about neutron scattering from heavy nuclei. So neutron scattering from heavy nuclei. So you have this heavy nuclei. And heavy, I believe, in terms of it's the position of the element in Mendeleev's table has a meaning. I don't know. The atomic number should be bigger than something, maybe 60 or 50. I don't know exactly. I don't know. But this is called heavy nuclei. So you hit with the neutron particle, N, and you see the scattering of this. So you get data, which is essentially energy levels of the scattered particles. And what they wanted to understand was so-called level spacing. Well, each of these guys is called a level. And then we have level spacings. So they wanted to understand if there is a pattern or there is a regularity in this level spacings. And for them, that was a way to understand the structure of nuclear force, basically. This is a problem in nuclear physics. Back then, they didn't have as much information as we do have today about nuclear forces and all these things going on. So they had a lot of data, and collected by experimentalists. And theoreticians wanted to make sense of this. And then this was attracted the attention of Wigner, who was a leading theoretician. So Wigner's idea was that, okay, I don't know what's the structure of this heavy nuclei. I mean, I cannot write a Hamiltonian for this like in quantum mechanics that you do. A hydrogen atom has Hamiltonians, and a lot of basically we know the Hamiltonian of all elements. I mean, because there are just electric forces between the different electrons. There's interaction term, and there is also central force term. So solving it is another issue, but at least we know the Hamiltonian. But in this case, you don't know the Hamiltonian. And so Wigner's idea was that, I don't know what Hamiltonian, so I just assume Hamiltonian is random. It was an ingenious idea. And another thing is these Hamiltonians in quantum physics, they're always infinite dimensional. He said, okay, I'm going to approximate it by finite. Okay? So he basically took a finite n by n Hermitian matrix. Now, why Hermitian? Because they know that the Hamiltonians should be Hermitian, because the eigenvalues, the energy levels have to be real, and these are Hermitian always. So his idea was that, okay, I take a matrix H, belong to some ensemble of matrices, so Hn, and actually the first ensemble he took was not even GUE, was a much simpler thing he took just to test what's going on. And okay, so that okay, then if I can compute the average density function of these eigenvalues, I have a chance to find the average spacing between consecutive things. This problem turns out to be extremely difficult to be solved, and it took about 30 years, 40 years to be solved. It was solved eventually, I believe, in 1980s. But what Wigner did several things. One of the first things he did was that he said, okay, I'm going to assume actually I have a 2x2 matrix. And then he wanted to understand the spacing, eigenvalue spacing between the two eigenvalues of a 2x2. And he wrote down an exact formula for that. I believe he had a proof for that. So let me explain his proof. So this is the birth of random matrix theory from nuclear physics. There is another connection to experiment, which is much earlier. I will explain that a little later. So okay, so now let me just right here. So now we are taking a matrix H belonging to H2. Oh, H2. So this is a 2x2 Hermitian matrix. And we have two eigenvalues, we call them lambda 1 and lambda 2, real, right? And what we are interested in is the statistics of distribution of lambda 2 minus lambda. We want to do distribution. Is what? Because both of lambda 1 and lambda 2 are random variables on this probability space that I put GUE, for example, probability measure on that. And then you want to know what is the probability distribution of this random variable. Well, so what we know is that by Boyle's integration formula, we know the joint probability distribution of lambda 1 and lambda 2. So Boyle integration formula is the JPDS. So this is a function of lambda 1, lambda 2. So let's call it P of lambda 1, lambda 2. This guy is proportional to, there's a factor of lambda 2 minus lambda 1 squared. This van der Monde determinant is only one term. Right? And then there is this Gaussian term, which is the exponential of minus. Okay, so I just put trace of h squared. Yeah, this one. Okay, so I mean, I can write trace of H2 in terms of lambda 1, lambda 2. So this is lambda 2 minus lambda 1 squared exponential of minus lambda 1 squared plus lambda 2 squared. So that's cool. So we have two random variables. We know the joint probability distribution function. Okay. And we want to find the distribution function of lambda 2 minus lambda 1. But the problem with this formula is that lambda 1 and lambda 2 are not independent. And, well, it looks like a difficult thing to do. But what we can do, we can actually go to a different coordinate system to separate them. So the trick is now it's always is like this. So let S, the spacing, the level spacing, is equal to lambda 2 minus lambda 1. And you introduce another variable, x be equal to lambda 2 plus lambda. We're trying to go into a good coordinate system now. It's like you have a curve, conic, which is in a bad coordinate system, there are mixed terms, and you're trying to separate mixed terms. So here, of course, if you solve, you get lambda 1 is equal to x minus s divided by 2. And lambda 2 is equal to x plus s divided by 2. Yeah. And the Jacobian of change of variable here is very easy. This is a linear transformation of Jacobian, which is determinant of d lambda 1 lambda 2 in terms of dsx. This is equal to 1/2. And also a simple calculation shows that lambda 1 squared plus lambda 2 squared, in fact, is equal to x squared plus s squared divided by 2. So by applying this transformation, you go from lambda 1, lambda 2 space into S and X space. So the probability distribution now becomes ESX, ESDX. Yeah. Right, so I just raised them. One question?
Well, I was wondering, it looks like the distribution is a Poisson distribution, which is kind of the difference of the eigenvalues could be related to the time between scattering intervals. So like if we integrated out lambda 2, we would get a Poisson distribution, I think.
Yeah, that's a good guess, but in fact, it comes sharply on the opposite side. It's not Poisson. So Poisson you would get if they come if they are independent.
That's true.
If they are independent, this is more or less a Poisson process. Now, okay, so there's a difference between Poisson process and Poisson distribution, but essentially Poisson in both versions, yeah. But this is not Poisson. It's something else. There is a repulsion. I mean, it will show actually in this case that eigenvalues again don't like each other. They try to stay away from each other. Yeah. But that's a good guess, yeah. Yeah, so let's finish the calculation. So we have got PSX, yeah, ds dx. If you do all these things, then you get this is essentially becomes a squared exponential of minus 1/2. Yeah. X squared plus S squared. ds dx. Now, you see, this is great because now we can take the marginal with respect to x. I mean, integrate out x, and then we'll get the PDF of s. So marginalize x, basically integrate out in mathematicians' language. The statisticians use marginals, integrate out x, then you get that actually PS ds is going to be same thing as s squared exponential of minus 1/2 s squared ds. There is some constant here, a. This a is essentially integral of the Gaussian. This is normalization. So you can find a by the condition that integral PS ds from 0 up to infinity has to be equal to 1, because this quantity is never negative, so it's always. Actually, you don't have even to stick to 1/2. You can put b here, because usually, now this is something in the statistics, so I don't have a good understanding, unfortunately. The data usually is raw, but then they do something to the raw data. They rescale it, and they what's it called, normalize it, so that, for example, the mean is shifted to 0, or there are some properties. For example, fluctuation is normalized to 1. They do something. And so there is this condition that integral s PS ds. So the average spacing they want to be equal to 1. I mean, so this means these two conditions gives you A and B. But it doesn't matter. The crucial thing is that there is a squared here and there is a Gaussian here. So what we have is that near 0 is a square, is a parabolic. Now, 0, first of all, at 0, and it's parabolic. Here is tangent, goes up, and then there is a Gaussian tail. There is some average is here, mu, but there's a Gaussian tail here, but here is almost s squared, because if you put s equal to near 0 here, it's very, very close to 1. So this is the dominant factor, s squared.
This is P of S, right?
This is P of S. And this is Wigner's sum. For GUE. So it's a well-known story that in the conference, Wigner was presenting his thinking of this neutron scattering. And then someone in the audience asked, okay, can you give us what is the distribution of this level spacing? And Wigner goes to the blackboard and writes down this formula for 282. So this is something historically is very important, because it puts into action a huge effort by Wigner. The first heroes of the game were Wigner, then Dyson, then Meta, Lal Meta, which is these are the original heroes, and then there were some other people. And then, okay, in 1980s, it really exploded. The subject random matrix theory exploded, and this problem that I said in general. So this was solved, I believe. There's a formula for that, which is. But all of these things start with Weyl integration formula, because this is a joint probability distribution, and you have to integrate out some variables, only remaining two. So the thing is, the analog of this trick for n eigenvalues, it's not clear what to do. It's extremely so. But you have to use this determinantal structure of the of the joint probability distribution and orthogonal polynomial method. But then there are some incredible identities. Basically, those identities are really all can be taught to undergraduates. They are identities about determinants. But yeah. Okay.
It looks like the same distribution as the Maxwell-Boltzmann for velocities in 3 dimensions. Or even the Stefan-Boltzmann too has a.
You're right. I cannot 100% confirm, but you're right. I have seen something similar to this. Yeah. Right. In the quantum case, right?
Yeah.
In the non-quantum, in the classical case, it explodes. But if you do the quantum, you get this actually. I believe so. Yeah. Yeah, there is.
But is it also like a quadratic and a Gaussian?
Sorry?
In the quantum case, is it also quadratic and Gaussian? I'm not sure.
In 3 dimensions, it is. Yeah.
Yeah.
It's very.
There is chi-squared. Huh? Are you talking about chi-squared distribution?
I was talking about the Boltzmann.
Boltzmann? Yeah. No, I don't know. Yeah, but I think I have seen something like that. Yeah, I think that's a good guess. Yeah. It has to be checked. Yeah. Now, if you look at, we did not discuss the symmetric case, the real case. You can look at real, well, I mean, maybe I call it SN. These are n by n symmetric matrices. There is also a Gaussian distribution on this. They have real eigenvalues, and you can do it for 2 by 2. As a rule, working with real matrices is much more difficult, as you know, than complex matrices. Real is simple, complex is real is complex, complex is simple, real. Anyhow. So for this, you get actually S. There is a linear dependence for real. And also the formula is known in the quaternion cases. This is according to Dyson's threefold way. I believe for the quaternions you get fourth power. Yeah. So these things are known, but they're more difficult to and there a lot of So we'll discuss a little bit of that. Yeah. So Now, what we want to do in the remaining maybe 10 minutes is to prepare the ground for generalized Hermite polynomials, which we are going to apply to quartic matrix integrals. And then we'll see some nice stuff there. Yeah. Okay, but I mean, mathematically, that's pretty easy. So let me.
Oh, is the coefficient b in the exponent the same as the beta value for the ensemble? So like the inverse temperature would be.
Yeah, that's right. That it is. Yes, you're right because indeed, yes, this is called beta ensemble, and these coefficients actually, yeah, in general, what we have is exponential of minus beta over 2 trace of H2, right? So this beta, but although I mean we have to be okay. So beta equal to 2 and beta equal to 4 and beta equal to 1 gives us this threefold way. But beta does not have to be actually an integer like that. Because in the formula that we have, you can just write product of lambda I minus lambda j to power beta. And while integration formula works in this case, and so people actually work with these things called beta ensemble. Yeah. Although, I mean, here we can understand this in terms of these two conditions. You see, if I just put 1/2, okay, so if I just put exponential of minus 1/2 raise of H2, as I was doing earlier, I have only control on one thing, right? Namely, this coefficient here, which comes from this condition. This, I wouldn't have any possibility to arrange this. So it means that in that case, the mean of the data, the mean point of the spacings could go anywhere. But then there is no way you can compare different sets of data to each other. To be able to compare them to each other, you need to fix also the mean spacing. So this means that your model should reflect that by putting here not just n over 2 or 1 over 2, some beta. So it means that you have a model which gives you a distribution satisfy both conditions. So this is very much kind of the statistics, the way statistics is done, which I don't have any good intuition about, I should say. So you should read it very carefully, but it is usually that's the way it is. Yeah. And experimentalists care about these things because if you have a data which is scattered in a certain way and another one, this doesn't make sense. I mean, it also depends on how many results you have. So, okay, so right. Okay, so this is about general. Yeah, but one more historical item I should say. So I should say I said that the birth of RMT was by Wigner in 1950s. So he has, I don't know, a couple of papers in Annals of Math and a couple of papers. So he has 4 or 5 papers, foundational papers of the subject. They're historical papers, which he does. So he drops actually this problem of level spacings, but he attacks the question of eigenvalue distribution and then drives Wigner's semicircle law. But that's not what in experiment they are interested in, because in experiment you never see eigenvalues themselves. You always see the differences between eigenvalues. And that's the difference. In the spectroscopy also, these are called they're called, what's it called? Spectral terms and spectral lines. The spectral lines, I believe, are eigenvalues, which are fictitious things in our brain. The spectral terms are the things that you measure, or maybe vice versa. So there are 2 things. And this was known since 19th century. You measure the difference between 2 eigenvalues, 2 energy levels. Always you measure. Because what? Because how do you measure that? Well, because you measure the energy of the photon, the frequency of the photon that's scattered. So it's always the difference jumps from one level to another level. So that's in the case of spectroscopy. I believe something like that also happens. And so what Wigner did, okay, was great mathematically, also to some extent for physics. But there was before that there was another guy, British guy, Bishard. 1928. He has also a very famous paper. So Bishard was a very good statistician working for the Department of Agriculture. And he wanted to know the correlations between different crops in each year. If you have like a good yield for, I don't know, barley and I don't know, wheat and I don't know, watermelon, what's this relation to other things, factors in the crop? So this is called multivariate. Yeah, there's a name for that in the statistics. So he put a model which actually is based on he created a random matrix really. He could not solve the problem, but interesting. Wigner actually mentions Bishard's paper. So he said that when he was thinking about these things, there was this book on multivariate statistics that's on his desk. It was open, and then he looked at one page and he saw this matrix just gazing at him. And he said, okay, I can take a random matrix, a different one, not the one that Bishard used. But some people say actually it was Hurwitz, 1890s. Because indeed Hurwitz is the first mathematician who talked about integration over compact Lie groups. I mean, for unitary, for this sort of thing. So what they didn't know about existence of R measures or all these things. He gave an explicit way of defining, integrating functions against a fictitious R measure. So some people say Hurwitz should be considered as the father of random matrix. I don't know. That's your choice. But that's enough history. So now we want to do generalized Hermite polynomials. Again, the goal now is to understand quartic matrix integrals. So phase transition basically in a quartic. matrix integrals. So, I mean, here the partition function of z is essentially like this exponential of minus, okay, we just work with 1/2, yeah. 1/2 trace of H2. Then there is this coordinate part, which is trace of H4. T trace of H4. Okay, DH. But you remember that this part we always called what? D mu of H, right? So it's like we have this, so this we have to see this as a potential term. So there's an interaction, four vertex interaction here. And this is the free part, the free term. So everything we have been doing was working with the free term. Now we have an interaction term. So we can just write it as okay, integral over H and exponential of minus T trace of H4 d mu of H1. Right? D mu of H. Okay. I mean, using again Boyle integration formula, this of course is equal to some constant Cn integral over Rn. Exponential of negative t lambda 1 to the power 4 plus lambda n to the power 4, right? This is this trace of diagonal times product of lambda I minus lambda z divided on term squared. Yeah. I less than j. And then d mu lambda 1. D mu. Yeah. So Cn, of course, we know, we calculated this Cn, the constant term before, is 1 over products of factorials, essentially. Okay, so d mu. Yeah. Yeah, Cn is 1 over factorial and minus 1 factorial. 1 factorial. Okay. So notice if t is positive or 0, this integral is convergent, right? Means rapid decay at infinity. So this is less than infinite for any t. So that's fine. So let's take this potential V. Yeah, we're going to finish soon. V of lambda, which is lambda 4. This is the potential. And we define an inner product. So we define a measure this time on it's basically exponential of minus t v of lambda is this function, this potential, and then the Gaussian times the Gaussian measure. I mean, for t equal to 0, we get the original measure that we put the weight we put on, but this is more general. And yeah, then we define inner product with respect to this weight. F G bar. And then What would my notation? Yeah, this not the notation is d mu v lambda. It's a perturbed measure, takes into account. And then you can use again this Gram-Schmidt process, right? Apply Gram-Schmidt. To this sequence one lambda squared, lambda cubed. And then you get a quartic Hermite polynomials. It's generalized Hermite polynomials, which are knowing them explicitly is more complicated. I don't think there is a very simple form to get generalized Hermite polys, which is fixed by the conditions that we had before. I mean, yeah, so we have these conditions that PV, we call them PV lambda, PVK. Lambda is monic of the VK. So let me call this PVK lambda, K from 0 to infinity. So by orthogonalizing this, we get this. And the second condition, of course, is that they are orthogonal. K and L is equal to 0. Right. So let HK, again, the important thing now is to use, to know the norm of each, norm squared of each vector. So we call this HK, inner product of K1. So, right? Yeah. Okay. So of course, I mean, again, we have same determinant story, namely, of course, 1, 1, lambda 1, lambda 1, and minus 1, lambda and 1 is equal to same if I put instead of lambda this pk thing. So p d0 lambda 1, p d0 lambda n, and then p d0 lambda pv1 lambda 1 pv1 lambda n, and then e d n minus 1 lambda 1 p b n minus 1. I mean, same proof that it is for Hermite function, same thing. So then what happens is that if we sub in this thing into this formula, you see, now we get rid of these quartic exponentials. So that's really nice. So we have the following formula then as a result. In fact, the integral of over hn exponential of minus t raised of h4 d mu of h is equal to now product of these lengths. So this is equal to Cn n factorial h n minus 1, h n minus 2, h, let's see. So, okay, so now we have to get some information about these things in order to compute this. But this is pretty good. It's a product because we are interested in log of these things. We want to take free energy, log of these things, and become sum of these things. So that's a nice structure. But getting these numbers is kind of hard. We have to use a recursion. And we do that. Yeah, and we also relate them to panel of A equations, which are nonlinear ODEs. They are very important in panel matrix. So yeah, and then we go from there. So I see you then on Monday. Are there any questions in class, in Zoom? Okay, so again, to read this, there's a nice account in Zwankin and Lando, the book that I suggested at the beginning, and also the paper of Ettinghoff, the notes of Ettinghoff. Very well explained and gives you a lot of insight. And of course, in any text, respectable text in random matrix theory, you will get this account as well. Okay. Great. So thank you very much. I say goodbye and then we'll see you later. Thank you. Bye now.